Column lapping is a crucial technique in reinforced concrete construction. It is a method that ensures the continuity and strength of the structure by overlapping steel reinforcement bars, commonly known as rebars, within a column. This technique involves overlapping rebars to create a continuous line of reinforcement. The rebars are tied together securely to maintain their position and ensure they work as a single unit. Rebars often come in standard lengths, which may not be sufficient to cover the entire height of a column. Therefore, lapping is necessary to extend the length of the reinforcement bars. By overlapping the rebars, engineers can create a continuous reinforcement system that spans the entire length of the column. This method is essential for maintaining the structural integrity of the column. Continuous reinforcement ensures the effective transfer of loads throughout the column, which is crucial for the stability and safety of the building. Proper lapping techniques help in achieving this goal. Column lapping is a common practice in construction projects of all scales. Whether it's a small residential building or a large commercial structure, lapping is used to ensure the strength and durability of the columns. From high-rise buildings to bridges, column lapping plays a vital role in the construction process. It is a technique that is widely used and highly regarded in the industry. Understanding and implementing proper lapping techniques is essential for ensuring the long-term durability and safety of these structures. Proper training and adherence to standards are crucial for successful column lapping. Proper column lapping is paramount for the overall stability and safety of reinforced concrete structures. When rebars are lapped correctly, loads are transferred smoothly and evenly through the column. This prevents stress concentrations that can lead to cracking or even failure. Incorrect lapping can have severe consequences. If laps are too short, the bond between the concrete and steel may be insufficient, leading to slippage and reduced load-carrying capacity. This can jeopardize the entire structure. Not all areas within a column are suitable for lapping. Engineers designate specific lapping zones where overlaps are permitted. These zones are determined by the stress distribution within the column. Columns experience both tension and compression forces. Lapping is typically avoided in high-stress regions, such as at beam-column junctions. The middle portion of the column, where stresses are lower, is generally preferred for lapping. Understanding these zones and adhering to design specifications is crucial. Section 4. Calculating lap length. Determining the correct lap length is essential for effective load transfer. This ensures the structural integrity of the building, allowing it to withstand various stresses and loads. The lap length is the length of the overlap between two rebars. This overlap is crucial for maintaining the continuity of the reinforcement. A simple formula is commonly used to calculate this length. Lap length equals bar diameter times development length factor. This formula helps in standardizing the process. The development length factor considers factors like steel grade, concrete strength, and stress levels. These factors ensure that the lap length is appropriate for the specific conditions of the construction. For example, a 16 mm diameter bar in a tension zone might require an 800 mm lap length. This ensures that the rebar can handle the tensile forces effectively. However, in a compression zone, a 640 mm lap length might suffice. This is because the forces in compression zones are different, requiring shorter overlaps. Section 5. Key considerations and alternatives. When implementing column lapping, several key considerations ensure its effectiveness. Proper planning and execution are crucial to maintain the structural integrity of the building. Staggered lapping, where laps are positioned at different heights, prevents creating a continuous plane of weakness. This method distributes the stress more evenly across the column. Adequate spacing between lapped bars allows for proper concrete flow and bond. Ensuring the concrete can flow freely around the rebars is essential for achieving a strong bond and overall structural stability. Mechanical splicing and welding are alternative techniques to traditional lapping. These methods can be particularly useful in specific scenarios where traditional lapping might not be feasible. Mechanical splicing uses specialized couplers to connect rebars, offering advantages in congested areas or high-strength applications. This technique can save time and reduce the amount of rebar needed. Welding, while effective, requires skilled labor and careful quality control. Ensuring the welds are done correctly is vital to prevent any potential weak points in the structure.